Let's continue chapter 4, looking at section 4.3, which is all about rotations. And in rotations, our first definition right here is a transformation which a figure is turned around a fixed point called the center of rotation. So pretty much what we're saying is we're going to take something right here, for example, like this calculator, and when we rotate it, if I rotate it around, let's say this point right here that I'm pointing at, we're going to take something, go counterclockwise, and rotate it around a fixed point. Now, this would be our center of rotation. The angle of rotation is how many degrees we would actually rotate something. We could rotate it 90 degrees, 360, 120, you name it. It all depends on the problem. Let's go ahead and go down to this next term of rotational symmetry, which is when a figure is turned and is on itself. So once again, we take this calculator right here, and if I go ahead and rotate around my center of rotation and I turn it 360 degrees, it'll rotate or turn on itself. Take a look at center of symmetry as we scroll down right here. Okay. So, in that first sentence, it says a rotation is a transformation in which a figure is turned around a fixed point called the center of rotation. Fair enough, we talked about that. Rays drawn from the center of rotation to a point and its image form an angle of rotation. So you can see right here, when we took Q and we moved it over to Q prime, this would be the angle of rotation of taking this whole thing and moving it 40 degrees. And then we go ahead and make sure we use, Q, Q prime, P, P prime to notate the original, and then also notating the pre-image and image. All right. Let's go ahead and scroll down, and we have a bunch of rules right here. The easiest way, just kind of like in 4.2, there were rules for rotating around the x-axis, y-axis, y equals x, y equals negative x. We have rules for rotation when something's being rotated 90 degrees, 180, and 270. We don't have one for 360 because hopefully you realize that when we rotate something 360 degrees, it is being rotated back upon itself. I have right there in a nice thick black bordered box, rotation is a turn around a point. It can be rotated clockwise or counterclockwise. Now, for most of our rotations today, we are talking about rotating counterclockwise. When I say rotating 90 degrees, it's going to be counterclockwise 90. If I said it's rotating negative 90 degrees, that's when you're going to be going clockwise. It's like opposite of what makes sense to us, but that's how it is. Okay, and we always start pretty much along this part right here of the x-axis, because this right here would be 0 degrees, and then we go counterclockwise 90, over here 180, down below 270, and then back at 360, or which is the same thing as 0 degrees. So it says for a 90-degree rotation, we switch, right? You can see that we switch A and B, and then we take negative B, all right, the opposite of B. For 180-degree rotation, you just take the opposite of A and B. And then for 270, once again, you switch again. However, you only take the opposite of A. So make sure, know your rules, remember them, your coordinate rules for rotation, and that'll make this section go by pretty easily. So in 4.3, this postulate right here, it mentions that a rotation is a rigid motion. Okay. Rotation is a rigid motion. So once again, the angles and the lengths of the sides will not change. All right, bottom line. Let's go ahead. It says graph the image of the polygon and after rotation of the given number of degrees around the origin. So when it's negative 180 right here, our rule is negative A, negative B. We just take the opposite. So let's start off right here. We got to know what our points are. So let's say J right here is negative 2, 4. We have K is negative 5, 1. Point L is negative 2, negative 2. And point M is at 1, 1. And these points I'm just getting straight from the diagram. Okay, so the rotation right here takes this to become J prime. And then we take the opposite of A. So opposite of negative 2 is 2. The opposite of 4 is negative 4. And there is point J. We have K prime will be 5, negative 1. L prime, 2, negative 2. And M prime is negative 1, negative 1. All right, and that right there is the rules and the points after the rotation. And so, let's go ahead right here. Let's plot these points. At 2, negative 4, we have J prime. At 5, negative 1, there's K prime. We have 2, negative 2 is L prime. And then at negative 1, let's go back right here. Things look a little funny, and I think you probably caught it. For K, let's see here. What the heck's going on? Let's see. 2, negative 4. There's J prime. We have at 5, negative 1. There's K prime. At looks like the problem right here is that I missed that negative 2. And so this is actually L prime is 2, 2. So 2, 2. There we go. I was like, this does not look like the same exact figure. And then right here at negative 1, negative 1, that would be M prime. So it always pays to be as neat as possible because it's easy to make mistakes. All right, let's go next to number 2. When we rotate 90 degrees, we have negative B, A is the rule right here. So we have, let's go ahead and we got R. Let's write the rules down. Point R is at negative 4, 0. S is at negative 1, 5. And T right here is at negative 5, 1. All right, so let's go ahead. We have R prime. We're going to switch it. Take the opposite. Opposite of 0 is still 0. And then A stays the same, so 0, 4. We have S prime. Okay, it's going to be negative 5, negative 1. And T prime right here is going to be negative 1, negative 5. All right, so we got our points right there. And I think you should hopefully be able to graph this out. So I'll let you do that on your own. And then for number 3, the rule right here happens to be B negative A. We got A happens to be at 1, 4, B is at 4, 3, C is 3, 1, and D is at 1, 2. So we have A prime. Okay. We're going to have B comes first, so we have B, and then we take the opposite of A, which is negative 1. B prime. We have 3, negative 4. C prime. We have 1, negative 3. D prime. 2, negative 1. All right, and there you go. All right, it says we got a composition here, and we want to try to figure out where is this going to be. Number 4, we'll go ahead and let's skip that. I think we'll skip 4, 5, 6, and 7, and let's go ahead and roll down to number 8. So we have, once again right here, a triangle. We got vertices J, K, and L. So first things first, let's go ahead and plot these points. So we have 2, 3. I think the easiest way for us to do this, let's say we could do intervals of 1. So we'll plot point J as 2, 3. So there's J. K is at 1, 1, or 1, negative 1. So there is K. And L is at negative 1, 0. So there's our triangle. Now remember, this is a composition. So first off, let's figure, all right, we got two things. We got a rotation around 180 degrees. So the rule right there is negative A, negative B. And so let's take J prime, and we'll take our points. So it'll be negative 2, negative 3. We have K prime, and we take the opposite of A and B. So we have 1, or negative 1, 1. And L prime right here is at 1, 0. So let's plot these points right here. So negative 2, negative 3, J prime. K prime, negative 1, 1. And then we have right here L prime. We have that 1, 0. So it rotated right here 180 degrees around the origin. Remember, the origin is at 0, 0. And that's how we ended up with our triangle now. Then finally, we are going to take these points right here. Okay? We're not going to take the original points because remember, this is a composition. This is when it's a composition, it's around several points, and x is equal to 2 is this wonderful red line right here. That is the equation for x is equal to 2, a vertical line. So lastly, let's go ahead and we have J double prime and we're going to take this and we're going to reflect it across the red line. And the easiest thing for us to do here is just to count things out. Okay, that will be the easiest thing to do. So we have this point right there, which happens to be, what is that? K prime, or no, sorry, this is L prime. So let's start with J prime. We count that as, look, how many units is it away from the red line? We have 1, 2, 3, 4. So 4 units to the left, that means it has to be 1, 2, 3, and then 4 units to the right, which would be like out here in space. So we'll go ahead and put J double prime. Now where exactly is that? We have 1, 2, 3, 4, 5. That'll be 6 and negative 3. Then we have K double prime. So where's point K? We have it at negative 1, 1. It's up here. So that is 1, 2, 3 units to the left. It'll be 1, 2, 3 units to the right. So it'll be 2, 3, 4, and 5. So we have 5, comma, 1. And it's positive. And then L double prime happens to be right here. It's at 1 unit to the left of the red line. So it's 1 unit to the right. 1, 2. So it's going to be at 3, comma, 0. And there you have it. We have this beautiful composition from points JKL to JKL prime and JKL double prime. Alright, so translation for number 9. Step 1, take points, plug it into that rule. After that, use the rule for a rotation of 270. The last thing we have here is this. Taking a look at number 10. It says determine whether the figure itself has a rotational symmetry. If so, how many? Describe any rotations that map the figure onto itself. So pretty much they're saying is this. If I take this right here, my calculator, if I rotate it 90 degrees, it doesn't rotate onto itself. But if I rotate it 180 degrees, it will rotate onto itself. If I rotate it 270, no. If I rotate it one more time, 360, yes. So it says determine whether the figure has rotational symmetry. In this example, it does. If so, how many rotations? You're going to take 360 because that's a circle divided by the number of sides you have. Or even better yet, divided by the number of vertices. That'll probably be easier. So if I take 360 divided by 4, okay, take 360 divided by 4, you end up with 90. But at every 90 degrees, that doesn't work out, right? So it'll end up being right here. Determine whether it has rotational symmetry. That is yes. At how many degrees? Well, if this was a regular figure, like, what I just told you with the 360 and divided by the vertices, I got a little ahead of myself, but that will only work if you have a regular polygon. So since this isn't regular, it doesn't work. If I had a square, and you take 360 divided by 4, so for example, a square divided by 4, remember you get 90. So at every 90 degrees, we have rotational symmetry. So let's put that together right here on number 10. First things first, this right here is a pentagon. It's a regular pentagon. So remember, it must be regular for us to use this rule. How do I know it's regular? All sides are congruent, all angles are congruent. So let's go ahead right here. I have 1, 2, 3, 4. I've got 5 vertices. So we'll take 360 divided by 5. And you will end up with, right here, 72. So if so, describe rotations that map the figure onto itself. It happens right here at every 72 degrees. Alright? Rotational symmetry, yes. When? Every 72 degrees. Number 11. Is there rotational symmetry there? Well, remember, it has to be a regular polygon, which it is not. So then the only way it'll rotate onto itself, hopefully you realize, is if we go ahead and rotate this 360 degrees. So you take it, rotate it 360, then it'll rotate on itself. The last one I'll show you right here is this. I've got my triangle. I put these measurements down. I happen to have a regular triangle. So we have 3 sides, 3 vertices. Let's take 3 divided by 360, and you'll end up with 120. So this right here in the triangle, if you rotate it every 120 degrees, then it rotates onto itself. There you go. 4.3, rotation. Keep on working hard. Make sure you guys follow along. Make sure you ask any questions in class if you have anything. And I'll see you next time.